Check sounds.
Hello. Yep, I can hear you, Peter.
Hello. Okay, yeah, good.
Mine muted so I could crash around beforehand. So.
All right, see ya.
Hi, all.
Hello. Welcome.
Hi.
Thanks for presenting for us.
Yeah. Let me mute it again.
All right. Well, hello, everybody. It's not a huge crowd, but hopefully somebody else will show up. So,
where is Ed?
So Ed and I were talking about doing this presentation together.
Yeah.
When you gave me the copy of LabVIEW 3.1, and I don't know if he's supposed to show up. I don't know if he signed up for the meeting. I'd have to look at the list. But he didn't really feel like he had a lot to present, so I just did this by myself. So, yeah.
I have a 3.1 Beamer that runs on that requires 32-bit Windows, right? So that's probably why you need a virtual machine. They're rare.
Yeah, it seemed easier to do it in a virtual machine try and do it in an actual running functional machine. It just seemed extremely painful. So
yeah, 32-bit Windows is hard to find these days. I haven't seen a machine in a long time.
Yeah, I haven't either. So But it does work. So
yeah.
it's a little bit painful to make it work, but it's not terrible. So let's see. I figured I'd wait a couple more minutes till more people showed up, and then so we've got a fair number now. So, and we can get going.
Yeah, definitely. I mean, who's starting? I mean, first you probably.
I listed you first, but you're welcome to go first or second. I can go either way. Which
okay.
would you?
Yeah, it doesn't matter. Yeah.
Okay.
Yeah.
Yeah. So, let's see.
So can you quickly tell me a little bit about the meeting?
Yeah. So this is every other month LabVIEW users group. It's been going on for, I don't know, maybe Petter knows, I'm not sure, at least 15 years. I'm a little unsure. I've been involved with it for probably 7 or 8 now.
Yeah, I don't know if I've been involved longer than that in these meetings. But yeah.
It's regional, right? More or less.
Well, it's the ALARM is an acronym for Advanced LabVIEW Users of the Rocky Mountains or something like that. So it's really for, the Front Range of Colorado. We occasionally get people come down from Wyoming, which is kind of surprising.
Yeah.
That's me. Hi.
Yeah. We get people that come from Colorado Springs on occasion. But that's about the sort of limit of it. It doesn't really go much beyond that.
Yeah, but now it's all virtual, right? So it doesn't really matter.
Right. It's all virtual now, and so it's very open to anybody that's willing to show up. I thought about posting something to the Reddit LabVIEW user group or Reddit forum or whatever you want to call Reddit's individual things, but I figured that would be a little overwhelming. So I skipped that.
Do you have a community group on NI or?
Yeah, there is a community.
I think
group
you have one, right? I haven't looked at it in a long time. But.
Yeah, it's. Let's see if I can. Let's see. Let's see. It's. Let me share that screen instead of this one. Let's see if I can. Where am I?
I was going to say, Ed Dickens is the one that invited me. I'm actually in Texas, but I work in the same company as him.
Okay, so I think I'm sharing, so this is the forums here. So it's just ALARM. This is the.
Oh yeah, the ALARM's user group. Yeah, I've seen that before. Yeah.
So, let's see, where did the controls for? Well, would you like to go first, Christian, or?
Yeah.
Okay.
If you want, I can start if you want, but okay.
Let me.
Does everybody hear me all right? I'm not sure how good that microphone is. I don't have a very professional setup here. It's just in the webcam. You hear me? Everybody?
Yep.
Okay.
Okay, I'm going to make you the host, Christian, so that you can control. You should be able to present now.
Okay.
That work? Yep, it says you're the host.
Okay. Oh, so I have to share the screen, I guess, right? Yeah. Okay. Let me see. I can close this Zoom meeting. I don't know if I need to keep that open. Okay, share screen. And I want to share the entire screen. That's easiest, right? I can go between PowerPoint and code and okay.
Yep, it's working.
Okay. Okay, so let me start here. So I quickly want to talk a little bit about memoization techniques today. I've been using these methods one way or another for probably the last 20, 30 years. And usually they make a big difference if there's heavy computation involved. And so let's just dive in and start to find out what it means. Ooh, let's see, I moved my signal again. Okay, so what is it, right? In Wikipedia, in computing, is an optimization technique used to speed up computer programs by storing the result of expensive function calls and returning the cached result when the same inputs occur again. So now how do we tell if a function is expensive, right? Where and how do we store a previously calculated result, and how do we efficiently find it again, right? The levels of complexity, you know, you can calculate once at compile time and apply simple transforms, lookup tables, interpolation, or scaling, or whatever, as long as you do, yeah. Or you can return the previous result if inputs don't change, like in a sub-VI. Or you can cache a few typical scenarios that are used all over the time. Or you can dynamically cache the last end results and overwrite the least recently used. There are other methods, you know, you can have like entries expire after a certain time, or you can have it do it the least frequently used instead of the least recently used. But I use the recently used, and I'm gonna show you an example how well that works. So the tools of the trade, of course, are shift registers. Is everybody here is probably very familiar with LabVIEW, right? And you used maps and sets before? Everybody? Or maybe? Yeah.
I haven't used them because I'm still stuck on an old version of LabVIEW.
Oh, I see. Okay.
They're terrible support for various industrial protocols that I need.
Oh, okay. Yeah. Okay. So, but you probably know what they are, right? I mean, I'm going to touch it a little bit. So we have shift registers, we have lookup tables, we have variant attributes. That's an efficient key value pair method. That's before LabVIEW 2019, and since LabVIEW 2019, we have maps, which is a much more flexible implementation of the same lookup, same dictionary implementation. It's just better in many ways and more flexible, or combinations above. And we're going to take a look at some examples from my field, which probably don't mean much. So the simplest way, if you have like a sub-VI, you know, and has a simple input and returns a complicated output, right? And if the input is always the same, do you see the cursor or not? I don't know.
Yeah, see the cursor.
Yeah, okay. So if the input doesn't change, you might as well not recalculate the inner code and just return the previous result, right? And so we need to balance is how expensive is it to determine if the inputs have changed, right? How often, if it always changes, you know, it's not worth doing anything like that. But if the input rarely changes, then it's very worth to cache it. So caching also has other advantages, and I'm gonna talk about that a little later, because caching like this guarantees that unless the input changes, all the calls have binary identical results. And that's not always guaranteed otherwise. So a counterexample, of course, if you have a large 2D array and you multiply it, you know, figuring first out if the array has changed or any of the input has changed, and then multiply it. You know, you need to look at each element twice at least, right? So you just do it, right? You don't need to do any caching, of course. So as a recap, right, the inputs rarely change in this simple example. Checking for input is very cheap. It's a comparison of a scalar with the previous. And we initialize with a sentinel value that's typically it doesn't occur, right? And if the same sub-VI is called in many different places, they all get the same binary identical result. The largest benefit is on the next slide. I already told you a little bit about that. If you look at that code, right, and here the only thing is the order in the compound multiplication node. All the numbers are the same, but if you run this, you see that once in a while some elements are not identical, are not binary identical. I have a link here. I will post the slides later. And so you can click on the link. It has been discussed in the forum many years ago. So even if the sort order here is the same of the input, and it's on different, and you do the same calculation in different places in different sub-VIs or in different places on the diagram, the compiler might still reorder it, and you might not get binary identical result. And if that's a part of a map key, that value, right, then you get a lookup failure if the value is different. So if you cache the result, then all parts of the program are guaranteed the same binary identical value. There is a second case, and that can occur very rarely. In modern CPUs, they do a lot of calculations internally on 80 bits to limit rounding errors. But if the OS swaps that out, it will be truncated to 64-bit. And if that occurs just at the wrong time, you might get a little bit flicker at the end. I'm not sure if that's the real explanation, but I found that on the web to explain some really rare cases where things suddenly are not identical. So caching the ramp in action that ensures that all code parts that depend on the output operate on binary identical values. I said that, right, which is very important when they're part of map keys. A single flip bit will cause a lookup failure. So that's always a controversial issue, depending on the age of the program and all that. You know, some like shift registers, some like feedback nodes. I actually like feedback nodes much better, but shift registers are much older. So if somebody has been programming for a long time, they're more comfortable with shift registers, right? So the feedback node does not require a dummy loop and has global initialization, for example, here, right? And so that guarantees that the recalculation is done on the first call. Whereas in a shift register, you have to make sure that it's also recalculated on first call, because these need to be uninitialized and you don't know what the values are from the previous run. But I mean, under the hood, it's the same, you know, performance is the same. Okay, so I tend to use the global initialized feedback node because it has the initialization built in. So let's go to a slightly more complicated result. That's my friend. He died like 5 years ago in Australia. He for our spectra calculations, you know, you have to integrate over all possible orientation in the sphere. Each orientation gives you a different spectrum. You have to sum them all up and so on. And so to calculate all these directions is a lot of trigonometry, right? And you might have to do 500,000 or so. So it's clearly good to cache those. Cache all these calculations, and then so up here we have the n, right, which is the length along one edge. This calculates all the directions in the x, y, z, all the factors and some weighting factors, because not all the solid angles are the same. And once this is cached, right, in the code down in the lower left, you see it here, it calculates the grid. And if the n almost never changes, it always outputs the same amount, the same value. And then here, this just can iterate over all orientations, multiply it with the tensors from the problem at hand, and generate the spectrum. So if you would need to recalculate that all the time, that would be quite expensive. And let me see. Oop, what's that? Oh, okay. Yeah, so, okay, so here, you see here is n. You see how it sort of fills that sphere with similar sized. I mean, you know, each area is very similarly sized. You have to account for edge effects and all that, but you see how it recalculates that. And typically you keep it the same most of the time. Now if you look at how a spectrum looks like, we can show the manifold. We can change the magnetic parameters, and if the line width is very narrow here, you see you get these wigglies because n is not large enough. This is 5,000 orientations. So we can go to 1,000, and now it's totally smooth. And yeah, the grid took 33 milliseconds to calculate, which is not bad. But once you use that as an inner function for fitting, you know, you have to recalculate the function many, many times. It really adds up if you can save like 30 milliseconds per iteration. Yeah, you see how the spectrum looks like, right? As a function of the magnetic parameters. This is completely uninteresting for anybody not in the field, but okay, so let's go back. Another thing is lookup tables, right? If you have a couple of measurements and you quickly need to get anything in between, right, you can also cache that. For example, you can cache that. That's also, somebody posted that in the forum. You have a list of torques and RPMs, and they're sort of all over the place. And by spline interpolation, you can cache the entire spline interpolant calculation, and then only recalculate for any RPM. You can calculate the point on the red curve. It's this, right? Oh. So, and of course again, so you can quickly calculate any value you want. Close this. So this is my field, EPR spectroscopy, and in one way, for example, we add labels to a protein and we measure a dipole evolution signal that's with nanosecond microwave pulses. And we get sort of a certain wave back, which is which is a collection of frequencies that depend on the distance between the two sites and their relative orientations and a lot of other things. And typically we have a distance distribution with multiple peaks and all that. So we need to somehow, from the measurement, we need to calculate the distance distribution, which is linear algebra, which is an ill-posed problem, right? It's the inverse problem. And for that, we need a big matrix that contains, for each possible distance, the infinitely narrow distribution over a time, right? And so let me, and again, this is very hard. This is a hard to calculate function because you have to integrate over many orientations. And so what you can do is after a while you notice that it's similar for all distances. It's just like printed on a rubber band. It's stretched or contracted, right? So you can do a very high resolution lookup table, calculate that once, and that doesn't matter if it takes a minute, right? And then you index and interpolate into it just with calculated values to get any other scaled form of that. It was, and so one example here is in this program. Yeah, I mean, this is just how this is what we measure, right? And then we get a distance distribution out. But if you look now here, internal data, if I change the number of distances, right, it needs to recalculate the entire thing. And I have an indicator here that shows, I mean, it's 60,000 elements, right, in microseconds. So there's actually only 36 CPU cycles per element. So that's much faster. And this can now be used inside model functions because it's so fast, right? If I go to like 1,000 distances, it's even faster because parallelization is more efficient right now. It's 17 CPU cycles. Anyway, yeah. Let me close this. Oh, okay. So a summary, that's an old slide from one of my NIV talks. So the lookup table is 10,000 times faster. You know, it takes 10 seconds to calculate that huge matrix, and it does it in now way under a millisecond on my fast computer. But once we have all these distance distributions, right, we can map pairwise, we can map a protein out. And one of the crucial results that was in 2008, we published that, is how the protein in the eye, the light receptor, changes as a function of light. It changes its shape, right? And we can map all these distances into 3D. So now the third way is we can use maps to store recent results, right? And I'm not sure how much I should go. I probably should go over quickly go over the slides because there's nothing new. This is from my old talk in 2019. So what is a set? What is a map, right? And what we did before, what's in the palettes, why are they so great? And where do they really shine? Performance, code, simplicity, both. A really great addition. And how easy is it to adapt legacy code? It's very easy. Okay, an example. So we have a new collection palette, and I guess Ben doesn't have that yet. Where we have build map, insert and remove from map, and so on. And you define a map with almost any data type for the key or any data type for the value. So that goes back to information storing for easy retrieval, right? An unsorted phone book is quite useless, right? And reprinting with each data change is also expensive. Sometimes people are crazy the way things are arranged. This is the panel in the old UCLA hospital. You know, if you want to go to level A, there are 3 equidistant buttons next to A. So you need to double take and scan it to decide what it is. So this is bad for lookup, right? If they're sorted according to number or to floor, it's much easier. So the same key concepts we have with maps and sets, they both deal with looking up information, right? Sets and maps are optimized for storing information and answering questions. Does the entry exist? If it exists, what is its value for a map? For a set, there is no value. They're optimized for dynamic changes in the data. We can add entries, we can remove entries, we can replace a value, and so on. And all these are much faster, even though it's not sorted, right? So a map is poorly defined in colloquial use, could be anything, right? In LabVIEW, it's an unordered collection of keys showing the same data type, in which duplicate keys cannot exist. Each key has an associated value. Duplicate values are allowed. On the map is basically a set where each element contains data. Value can be of almost any data type. You can have a cluster or anything. The key also can be almost any data type, right? You can have a key can be a cluster of many different values, and you can put it in as a key and a value some other cluster. And if you then later ask, does that key exist? It will return what was stored under that. So maps, there are many terms for the same thing. It's a map, associative array, symbol table, dictionary, right? It's known under many names. And the classic computer science problem is to design data structures to efficiently do operations, lookup, insert, delete, right? And that's 10 years ago. I made that suggestion in the idea exchange, and finally they put it in. So good arrangement of data can facilitate operations, right? For example, if an entry exists, can be improved by storing in sorted order. Assume a set with 1,000 entries. We must prove that a certain element does not exist among these 1,000 entries, right? If we have an unsorted array, we need to inspect all elements to prove that it doesn't exist. If we know that the array is sorted, we only need to inspect 10 elements, log 2n, right? Each inspection eliminates half of the remaining entries. That goes really fast, right? The problem is, and entries are added or removed, resorting is needed, right? And how do you manage the memory and all that? And where do you store it? And how do you look it up? The solution is efficient data structures where rebalancing is cheap, and that's a classic computer science problem that's over 30 years old, right? In '78, Robert Sedgwick first published a red-black tree structure. It took him 30 years to improve it slightly, but others say, yeah, you don't need fewer lines of code. It needs to be faster and so on. So, but we don't need to worry about that. LabVIEW sets and maps use standard public libraries under the hood. It's well tested and optimized, and they just integrated really well in LabVIEW, and the performance is fantastic. So I wrote a long time, you probably, maybe you've seen that I made an example for a set where we can compare different methods of looking up if something exists in a collection. And the example is we generate Lodo numbers until we find one that is one that we already generated earlier in that same run. So we need to keep all generated loader numbers as we generate them and compare each new one with all old ones. The worst case lookup, because entry is not found until we stop. It's surprising, you know, any given loader number, it's impossible to ever generate any particular one. But if you generate so many, each new one you compare it, so there's so many old ones that it's actually relatively quick that a duplicate is found. So I made four codes: linear search, binary search, variant, and set, right? And this is just a loop that stops once an entry is found a second time. This generates n loader numbers, right? With the string array. Now we have to flatten that array to a string, add it to the end of a string array, and then always search the entire array to see if it already exists, and when it exists, it stops. Now for the map at the bottom, right, we generate the keys, and the 2D array, the 1D array of loader numbers can be directly a data type for the map, for the key, right? We don't need to do strings or anything. With variants, we had to do strings. And once the entry is found, we stop, right? And here is sort of my own thing, which does a string array. And let's go on the next page. What this does is smarter. What it does, it searches the string array using a binary search. It assumes it's sorted. And a single binary search answers two questions. Does the entry exist? And if so, where? Or if it does not exist, where do I have to insert it into the array so the array remains sorted, right? It's a sort of memory trashing, because that array grows all the time, and when you have to insert, you have to move everything up. But it's much faster because we can do a binary search, which again reduces the number of candidates by half with every single lookup. So if now go here, so I rewrote that. I presented that in Austin in 2019. I rewrote it completely. But so what we do now here, we have these four different things, and it alternates between them. And whenever somebody takes too slow, it cuts it off. But if you now look here, if there are 1,000 entries, we don't know how long it takes, right? Because it's lottery numbers. But when we find it, if we then look how many tries it had to inspect it, right? We can calibrate that into a XY graph. So if it found it after the 1,000 entries, you see that the string, the append, is only 4 times slower. So it's pretty good. But once you go to like a million, right? Now it's 12,000 times slower, right? It scales very poorly. So the maps and sets are both very similar. Depends a little bit on the CPU, 33, 34 milliseconds. Sometimes the map is faster, sometimes variant attributes. And my thing that does the binary search is pretty close for the slower thing. It goes up a little steeper back here. And if you look at the slope here at the cursor, and that's at the slope on the log-log plot, these are all close to 1. That means it's really efficient, whereas the other one goes to a slope of 2 or more, right, that means for every doubling you get, it takes 4 times longer. So it really gets tired very quickly. Sorry. Well, I don't have water. So so I spent a lot of time to write a map-based code, map-based cache, and I can share that code with you guys if you want to look at it. So since maps are so efficient, it is tempting to use them to store past results with the assumption that eventually we'll need that same result again. The parameters are the key, right? Whatever the data type is, the value is the result based on these parameters, right? And we only need to do it if the calculation is expensive. The problem is if we blindly add every result to the map, things will become slower and slower, and eventually we will run out of memory. So the question is, can we add some housekeeping to discard entries that have not been used in a while, least recently used, for example? Other possible modes, least frequently used, or a fixed lifetime per entry. That means I add it and I want it to expire a minute later or whatever, right? So my special implementation, the key is a string. It doesn't have to be, but that's it was easier to replace my old variant attribute-based code with that. The data is a 1-bit array of fixed length, which is my spectrum. The defined size is the size of the data and the number of entries. And it's the least recently used cache. And usually I do like 4,000 entries or so, and it's really fast. So the modes are customized for my use case, and I explain why I need this. It's for parallelization, right? We have one mode is init. We have a lookup entry by key if it exists. Else return not found or reserved. We can add an entry, and that will almost automatically discard the oldest, or the ones least recently used, yeah. We can reserve an entry. If entry does not exist, add a key. So the key exists, but the data is marked as invalid. And that's for parallelization, right? We have all these tasks that need to be done, all the spectra that need to be calculated. And so each parallel worker basically goes, checks out the problem and say, okay, I'm working on that. Nobody else should work on that. So it needs to reserve the key, right? These parameters. But once all the parallel workers are finished, we have all results will guaranteed be available, and we can assemble the final spectrum. And every access, a lookup, an add, and a reserve for a certain key will rejuvenate that entry, will put it in the younger than all the other entries to make sure that it doesn't expire. If you look it up, if you add it or if you reserve it, you're going to make sure. If you reserve the oldest entry, right, and then some other guy adds it, it will be kicked out. So we need to make sure that we reserve it. So the code is available. It would be easy to modify for other data type. It's really specialized for my use. Let me see. Okay. So let me see where we are here. So here is. I'm not sure how well you see that. So this is basically, this is the code. This is one VI. An action engine has these modes, these various modes that put spectrum in it, And then here, this is the function calculation, and this sort of mimics what I do with the spectrum. It takes all the keys, and these are the set of all the spectra that we need to calculate the parameters, right? It's a dummy function. It's not really mean anything. And so we have a parallel for loop, and for as many parallels as we have, each one, as soon as it gets it, it reserves the entry. And then if it does not exist, it will calculate it and put it in the cache, right? And the next parallel instance will get the next one, and that might already exist, right? So it will just ignore it. This already has rejuvenated it, and will go to the next iteration until all sets are calculated, right? And once all spectra are guaranteed to be in the cache, we use a second loop, and we just grab all of them, again, based on key, sum them all up, or whatever mathematical operation we need, and we get the final spectrum out. So it's basically just a fancy way to make sure that we can really parallelize as much as we can. So if we look at this now, and I'm not going to go into it, but there are test scenarios here, what you can try out. For example, it's 32 times faster at the moment, right? We have a 4,000 cache size. We have 512 static values, and it picks randomly 128 out of those. If the cache is smaller than the number of static values, we always lose a few, right? And they have to recalculate those. So if we do like only 100, right, then you get constant cache error, and it takes slower. 4,096. So this is, we can say, a probability where it generates something that it's not part of the static values, right? If that's 0, we're 1,000 times faster. If all entries are always new, then the only gain we get is the parallelization, and this is a 8-core, and you actually get 14 times faster than a single calculation. You can turn off parallelization, and now we're down to 1, right? So here, all the spectra need to be calculated, but since we do it in a parallel loop, and each instance calculates its own, it will be 8 times faster. And this is, yeah, the function is just a burner function, basically. I mean, it's pretty dumb. Why can't I open it? Oh, here. No. Oh, I know why. It has to be a reentrant, of course, right? And somehow it goes off, it opens off screen. So, but you can look at it. I will post the code later. But let's look at the cache. Very simple code. We have our shift registers, and we have the keys. And if you look here, here's the spectrum cache. So the map actually only contains an index into a fixed size array where I have all the spectra. And then the age lookup is also actually done with a second map. Yeah. Yeah, I mean, I'm not going to over it. You can study it and ask me questions later. This maintains the age. So the problem is we need a reverse lookup, right? We have to find the oldest entry, and if we search, again, we run into slowness. But if I use a map-based, I can actually, there's a function called the largest and smallest entry that almost immediately tells me the oldest entry to be discarded, and the newest entry plus 1, it's just an integer, right, will be the age of the new element. Okay, let me close that. So yeah, I mean, you need to study it. I mean, it is impossible to present. So in my case, what I need to do is I need to calculate many spectra in parallel, maybe hundreds of spectra with many parameters. And some spectra depend on some, other spectra depends on other parameters. Some depend on none for particular iteration. And for the partial derivatives, some of them don't change, right? If one spectrum doesn't depend on one particular parameter, the partial derivative is the same, is 0, right? So it would be herding cats to try to keep track of all that. So it's easier to do it in parallel and do all the cache entries. And so we create n unique named copies of the DLL. The hard calculation is actually a Fortran DLL, which is very old, very complicated code. And then we call it by using the parallel instance. The Fortran DLL is not re-entrant, so we have one on first run. It goes into the temp folder and creates n uniquely named copies of that DLL. See, with a name. And if it doesn't exist, it will copy it there. If it's already exists, it uses it. And then here's the parallel instance ID. I'm not sure if you're familiar with that. You can right-click, and instead of show the P, you can do show the ID. And that's required because each parallel instance ID has its own, has a uniquely assigned DLL as a worker, right? So we get the spectrum here and know the path of the DLL, of any particular DLL, based on the ID. And then here we just iterate over all parameter sets. And if it takes a long time, I can optionally show the progress, which pops the front panel, which has a progress bar, which is, of course, a little harder in a parallel loop because it would jump all over the place. So there's some extra code in there. But if you look in here, the only thing it does takes the DLL path, calls that DLL, it takes the parameters, masks out parameters that are not needed or unimportant, for example, scale, right? You multiply it later. We don't need that as a separate parameter. So it sets those to 0, creates the key by flattening all the settings and parameters, and reserves the entry. If it doesn't exist, it calculates it. If it exists, it just say, okay, make sure it doesn't expire, so we rejuvenate it. And that happens automatically, the reservation. So if it needs to calculate, it calculates it, puts it in the spectrum, and again, that rejuvenates it again. Very simple, right? And if you now run that on a machine with many cores, you can see that, like, compared to if you run it on one core is the blue line, right? Now it basically scales with the number of cores, right? This is an 8 core, it's 8 times faster. This is a 16 core, it's 16 times faster. And I don't remember how many cores this one has. And all cores are 100% occupied doing real work. And AMD is really good again. They were really bad for a long time. That's the new Ryzen. And I can show you that quickly. Let me see. So this is the program. So I'm not gonna. Yeah, here you can. Yeah, it can fit, right? And if you look here, we can go here and benchmark, and it does 3 different runs. It runs it on one core, on all available cores, and then in a third run, it makes sure that everything is cached and doesn't need to be recalculated, and you can see that it's like 1,000 times faster, 1,300 times faster. And this is 8 cores, 8.4 times faster because they're hyper-threaded cores. So once we allow all cores to operate, it's 8.4 times faster. And the cached, this is basically the cost of the critical section. You can see that it's completely irrelevant. I mean, here it has to do all the lookups, make sure it's in there, and so on, right? And refreshing the entry. But yet it's 1,300 times faster. Curious, my earlier implementation, variant-based, was only about 400 times faster. So I'm gaining a factor of 3 or 4 here, which is irrelevant currently, right? Because it's such a small percentage. But once you have many more cores, the critical section, they tend to step on each other's toes more and more, right? The more cores, the more workers you have. So it might be better maybe in 10 years or so, who knows? And so that's it. How are we in time? Oh, we're good. 1 hour.
It's beautifully timed.
Yeah. So I just scratched the surface. You know, I can't really go into details. I try to keep it extremely simple, you know, but some of those are complicated problems. But I mean, feel free. I will probably give the link to Ben to download it. I have to download it from my work computer. So yeah, I will zip that up, the cache. I already gave it to the champions, you know, just to try out, just make sure it's useful.
I'll post it up to the alarm page.
Yeah. Okay.
So.
Yeah. Yeah, and I can post the slides too. So I zip up the slides. I mean, the other programs, they're available there online, but they're not of interest. Okay, so let me see what I do here. Oh, stop sharing. Yeah. Okay.
Thank you so much.
Yeah, thank you. That was really excellent.
Thank you.
Let's see.
Yeah, the problem is I do pure math, right? I'm not into instruments or anything, which is sort of really unusual for LabVIEW, but it really works really well. I've been using it.
That's kind of, it's kind of. It's kind of interesting because everyone says no, you can't do it with LabVIEW because LabVIEW is not the right language for those kind of things, right?
Yeah. No, I mean it works so much. It's so much better. You know, I have some friends that do similar things in MATLAB, and they're always slower. And it's much harder. They have fewer features because it's harder to debug. But I mean, they're getting there. But I mean, clearly my programs are more popular because they're so interactive. right? With MATLAB, I mean, they now built a sort of a set of tools for a lot of these things, and they actually took a lot of my ideas. I talked with the author about what I do, so they implemented some libraries. But you have to write your own MATLAB program, right? It's just a toolkit and assemble it all, and not everybody wants to do that. My programs, you install, you run, you put your data in, that's it. Yeah. But
yeah, I don't remember. I haven't used it in probably 25 years, MATLAB. Is that the what do you call it, interpretation language? Is that, or is it compiled that also?
I think it's compiled, yeah.
Okay, yeah, all right.
It's pretty good, you know.
We have some
curious
MATLAB.
That the MATLAB, the guys in MATLAB, just like 2 months ago, they moved everything over to Python. So the entire toolkit is in Python and is no longer MATLAB.
What?
Very interesting. And now I can actually put it in LabVIEW with the Python toolkit. Right.
Well, that's going to be slow then, right?
On the way down. I don't know. Okay, so Ben, do you want to give your presentation, or?
Yeah, I reclaimed the host, so
okay, cool.
Let me get it a little bit.
Gotta move my.
Let's see. Share screen. It's weird that. All right. All right. Well, thank you, Christian. That was really interesting. I'm a little vague on what I do with it, but it's great. So can everybody hear me, I think? And so I have something in the other direction. The oldest, I had an amusing idea a while back, is how old of a version of LabVIEW can I get working on a PC? And Ed, who is unfortunately not here today, was helpful enough to help me with this. So it's a little weird. It's a little fun. So why would anybody want to do this? Lots of us have old code laying around. It's a little hard to get to. If you haven't brought it forward, it's pretty painful. So this is a good way to look at old code without having to try and port it up forward to a modern version. So it's also kind of fun. What things have changed? What things have gotten better? What things have gotten worse? Fortunately, not a lot there. And vintage computing's kind of a fun hobby to get into. Not sure that I'm into it beyond this. Actually, I have an old Macintosh. It's pretty terrible too. So, so lots of fun there. So how do you get ancient copies of LabVIEW running? You need something that'll run DOS. And there's a couple choices out there. And I'm cheap. This is just for fun. I don't need to spend any money on this. So what's free out there? And the obvious choice is DOSBox. DOSBox is super easy to get running. The problem with it is it's not really an implementation of DOS. It's a weird modern hybrid thing that talks to your file system directly, but it won't actually do things properly. So you can run Windows on it if you want, but I could not get LabVIEW to install, and I'm a little vague on why. So I chose VirtualBox. It's out there, it's free, it's fun to play with, it's easy to use. So it's a pretty nice system. So many years ago, I owned Windows and DOS, Windows 3.1. I think it was actually 3.11 or 1.1. I don't remember exactly what it is. Windows for workgroups. And I don't ever recall giving up that license. I didn't sell it to anybody. So, how do I get it? There really wasn't licensing back then. There wasn't a key you had to type in to prove that you had a legitimate copy of Windows. But the internet's to the rescue, and there's this really nice website, winworldpc.com. And if we click through to that, this website has got all kinds of old stuff. It's got OSs, applications, games, development tools, all this stuff. And stick around in here. DOS is right here. Windows is right here. So old versions of Macs, all kinds of stuff. So these guys will let you just download it, pick your version. So I picked, I don't even remember what I picked, 6.22. And it's just pick all kinds of versions and all kinds of stuff. So pick what you want to download and have fun installing it. Am I violating some license? I don't think so. I used to own a license. I don't think I still own it. So, so onward, how do you actually get DOS running in the virtual box? And it's a little unobvious. You'd think that Windows would be a choice here instead of other, but it's not. So let's go ahead and look at that. The virtual box. So say new here, and type a name. You'd think Microsoft Windows would be a sensible thing here, but it's really not. It's really not the right choice. So choose other. What did I do wrong? I guess I clicked one too many times. And then choose other here and choose DOS there and give it a name and place to put it. This is the default place. And what did I do here? And the other setting is in here under system/motherboard, make floppy the first boot device. Oh, it's my running, so. Just hit next through all these things here. And you want this VDI virtual box disk image. So now we've got this, obviously done something wrong there. Anyway, but the important part here to the other setting is under storage. Wow, I've totally given this up. Under storage, you'll have a floppy drive. I'm sorry, under system, you'll be able to choose, make sure that floppy is your first device because you're going to be installing everything from virtual floppies. So, so that's really the only setting you need to make inside of it well, there's a couple more. There's this, if you remember, old versions of Windows are 800 by 600 resolution, which is pretty tiny. So if you don't go into here and choose this scaling factor here, if you just leave this at standard, you'll get an 800 by 600 screen that's extremely unusable in your modern high resolution screen. So you don't have to change, just pick a perfect number now, but definitely change it to some bigger number. It's easy enough to do. It's nice to make it work, to make it usable. And like, I remember my old Windows 3.1 machine had at the time, a nice monitor, and it was a pain to install drivers and get it working at the full resolution. But it might be possible to do that here somewhere in maybe these settings here in the VM settings, or allocating memory, and then you have to go somewhere into Windows and change the settings. But I never got that to work. So, but 800 by 600 really gives you the full experience of a terrible tiny monitor. So it's a lot of fun that way. So what do you have to do to install DOS? So that's why I had you choose floppy as your first boot device, and go and grab Windows, whatever version of, not Windows, but whatever version of DOS you wanted. And it's typically a zip file, and inside of that are 4 .image files. And each one of those is an image of the original installer disk. And so in here, you go into storage and just choose a disk file. Let's see. Where did I put it? Why is this being terrible? There we go. So pick the first one, and then go ahead and start your VM, and that will boot into that DOS installer. And you'll get prompts that, if you've ever installed DOS before, is pretty familiar to you, but just sort of work your way through them. So there's only 4 of them, so it's not terrible. And it'll prompt you, and so you can do this live with the running VM. You can go in here and change to the next disk. And I'm not going to do that live here. So just go ahead, and when it prompts you, insert disk 2, go ahead and insert disk 2 and work your way through them. It's not terrible, but it's, and eventually you get a DOS prompt. And from there, go ahead and install, download your version of Windows that you would like to install. And inside of that, go ahead and choose that first disk of Windows. And strangely, they're a slightly different name, disk 01. So pick that, and then in your DOS prompt, let's just go ahead and try that for now. This is actually the running one. So inside of there, you can change to your A drive like you're used to, and run setup. And that will start installing Windows, and it'll prompt you to go through each of those disks in turn. And there's 8 of them, I think that's what there is. Right, there's eight disks to install Windows, and at the end, you'll have Windows running, and it prompts you to set up a printer or a network. I just skipped that stuff. And at the end, you've got classical Windows 3.1 that you're used to, or maybe you're not. Hopefully you're not. One of the things you can do is inside the autoexec.bat file, which is in there somewhere, I don't quite recall where, you can just add the command win, and it'll start Windows for you, so you don't have to go and get Windows running every single time. So then comes the really painful part, is installing LabVIEW. So Ed gave me, he had obviously just taken the disks and just used an actual floppy drive to copy all the contents of those disks in individual directories. But VirtualBox won't let you do that. It won't let you access the file system directly. So you need to turn them into something else, something that VirtualBox will accept as a floppy drive. So, or a floppy disk rather. So I looked around and I found this program, WinImage. It seemed like it was free, but now it's a 30-day trial. So if anybody has a better way to do this, I'm willing to listen. So inside of WinImage, say new, and you get to pick what size floppy. So it's just your classic old 1.44 megabytes. And then go and find all the files for that, each disk. Just drag them on there. And then save them. You'll say save, and here you'll select virtual floppy image and where to put that. So we'll call that disk 1. And I don't know that there's a better way to do this because there's 16 disks to LabVIEW. So I just went ahead and powered my way through it and did all 16 disks individually. Let's see, did I miss any? So I don't know any way to automate that. If anybody's got a suggestion, I'd be happy to hear it. And then in Windows, just go ahead and under main is your file manager. And well, I failed to put the disk in. So let's go put the disk in. Settings, storage, floppy. So here's your LabVIEW installer, and just double click on setup and it'll prompt you to go through all those disks, and eventually you'll have LabVIEW installed. And it prompts you to install GPIB drivers and stuff, and I just skipped that step. I'm not sure how I would even conceptually get GPIB working in your virtual machine, so I just skipped it. So let's try it. What's DOS like? What's Windows like in the modern age? Windows 3.1. Let's this junk here. So it's an interesting experience to look at Windows again after a few decades of its changing over the years. And there's some pretty obvious stuff that's missing, like where the heck did that start menu that we're all used to go? It's just missing. And it's kind of weird to have it missing because everything is right here in front of you. And there's no sort of, what's running, what isn't running, how can you tell? And so first of all, what is this? Well, it's kind of strange. File manager. There's a lot of weird stuff sort of tucked away that I can't quite recall what it's for. Like, what is this? Smart monitor? I have no idea what it does. So there's a lot of strange things tucked away in here. Let's see. You can't make shortcuts on the desktop, or the desktop doesn't even really exist. It's all sort of desktop and nothing else. So that's kind of awkward. How do I get to something without clicking through these menus here? And maybe it's possible, I'm not quite sure, to sort of make a single item here. Another weird thing is right-click doesn't exist. I'm right-clicking, nothing's happening, at least not in Windows itself. It exists in LabVIEW, of course, because that's what LabVIEW is. The mouse wheel's not supported, which isn't too weird, but is kind of in a way, because you kind of think as mouse wheels just sort of, some level, just pushing page down or the down arrow or something, but it's not, it's doing something else. The other things that I find weird, you know, here, if we're in an application, we're very used to there being an exit button up here. There's only the minimize and maximize buttons. So you always have to go noodling around and go find the exit like this for everything. So that's pretty weird and irritating at some level. So the other thing, if you want to get out of Windows, it doesn't do any sort of safe shutdown. You just do exit Windows. And you know, in a modern PC, this would shut the PC off, but here it's just back to the DOS prompt and you just virtually push the power button and you're out of Windows. So that's pretty strange. Some other things that are interesting. There's no programs directory anymore, and I'll show you that in a second when it's done rebooting. The programs directory hasn't been invented, so you know there's a LabVIEW directory just in the root, which is pretty strange. You know, why is it there? So it's neat to see how things have changed over the years and gotten more organized and more transparent about how to do things. And I think that's pretty neat. Does anybody have any questions about just how Windows itself is working?
That was like 1994, that stuff, right? That was.
Yeah, it's somewhere around there. I remember buying my first computer in 94, 95, somewhere in that area, and it was pretty pricey back then, and you know it was a significant investment. And nowadays, you know, a computer that's entirely adequate for goofing around on the internet and checking your email is a few $100s, and at the time it seemed like in 94 I spent a few $1,000s and got something that was basically what we're looking at right now, a low resolution screen, and everything was very manual. It was very complicated. You did, oh, I'd like Windows to start on startup. I have to go manually edit, this particular file to cause it to happen.
And that wasn't that Netscape? What was that? There was a browser also. I mean,
yeah, there was a browser, and it's probably right there on this WinPC world.
No, TCP/IP was not even supported. You had to do some third-party WinSock, right?
Yeah, it was an absolute. I remember it was an absolute pain to make that work. It was incredibly painful. You had to install something, and then this WinSock thing, and then and everything was dial-up, and so everything was sort of, it's consuming. I can't use the phone because cell phones didn't exist yet, but I can't. Because I'm trying to get on the internet, and then it would take.
Oh, it's the same with Verizon still.
Yeah.
I haven't come any further than that.
Yeah. So, where is AutoExec? Is it in here?
Yeah, back then I was actually on the beta for Windows 95.
Wow.
21 floppies.
Yeah. So, we could.
And that was a big progress, with the start menu then. Yeah, so your 3.1 should run on the Windows XP actually.
Oh, yeah, I'm not sure. Yeah, I haven't tried it.
I actually put a link in the discussion.
Okay.
I have it running, but it's just a 3.1.1 demo.
Okay.
From National Instrument. I have some old floppies, and that run fine on XP 32-bit.
Okay. Wow, yeah. I hadn't thought to try that. It's more an exercise in how ancient version can I make it work at all.
Yeah.
So it was kind of fun. So let's go ahead and try LabVIEW, because that's what we're here for. We're here for horrible versions of LabVIEW. So here's it gives you a LabVIEW program group. I'm a little unsure what to call these anymore. So I don't have a DAC card, so I'm going to ignore that. So good old LabVIEW. So it prompts you for this registration. I don't have a serial number, and it doesn't seem to be required, which is pretty weird. You know, why isn't it required? But it's not. So hit OK. It's not been registered.
Yeah, for many years you could make your own serial number. It just had to be letter, number, letter in a certain number.
Okay, I had no idea. Yeah,
Everything worked.
Yeah, I got into LabVIEW probably version 8 or so. I'm a little unsure. It was probably 99 or 2000. So I'm not sure what version was the thing.
Let's see what you got. Is it 3?
Yeah, yeah. So you click through that unregistered user, and it automatically opens a blank VI for you. And it's a heck of a redraw there. So, and it opens a diagram automatically. So we're all used to either using the auto tools thing that switches between the the spool, the wiring thing, and all those different things for us. And I don't know what most people do, but I usually leave that in auto mode unless I'm trying to do something very specific or picky. Well, auto mode doesn't exist. It's all right here at the top. So that's pretty weird.
There is no undo. There is no undo.
Everybody mentions that, and there's no undo, and it will drive
I hated that.
you.
I hated it.
It will drive you crazy, the fact that there's no undo. So.
And then it crashed. Oh.
Yeah. I haven't actually had many problems with it crashing. Some other stuff that's interesting, right click. Everybody's used to right click working like left click. You click once, and it opens whatever you've clicked on, and then if there's sub things to click on, you move to where you want to click, and you click on it. Well, right click works differently in this iteration of. I'm not sure if this is a Windows thing or a LabVIEW thing, but if you just single click, it's like you have to hold it down. So I'm holding down now, and then scroll to exactly the thing you want, and then let go. That's a very strange workflow at some level. Like, why is this totally different? And it's absolutely maddening to use because you're very used to, it operating like the left click. So.
The Mac only had one mouse button.
Right. So, yeah, and I've Windows back then, or LabVIEW was originally a Mac program, wasn't it? I believe, and it's interesting that sort of neglected at this point. It exists, but it's not nearly as well maintained. So. Some other things, there's in decorations, there's no way to make a sub panel, so that's pretty frustrating. At some level, I use sub panels fairly extensively. Other things here on your diagram, Visa doesn't exist yet, so all of your instrument stuff are individual calls, serial. Visa's there, but it's not, it's a little vague what all this Visa stuff is about. So it's pretty strange. And then this is something that I find really bizarre. So I've put a numeric here, and it's an input control. And if I want to switch that to a indicator, I can change that to an indicator pretty easily. Now it's an indicator, but there's no turn into a constant. So that's pretty weird to have missing. So if I want a constant, I have to go find the right one over here. And now I've got a constant. But it is neat. Some of these things are identical that you're very used to. Representation is the same thing it's always been. Let's see. The other things I found that are interesting, attribute nodes do exist. So I can right click on this, I think I have to go from the front panel. So create attribute node. So that's neat that you can do these attributes still. And it's not nearly as complete as it is nowadays, but it's there. You can do it. So that's a kind of a neat trick. The other thing I really was interested in looking at was quite a while ago, I was at one of my vendors' facilities, and they're running LabVIEW there, and they had written the cast function from scratch. They were converting from a series of bytes they pulled out of a serial port into a floating point. And if you're familiar with floating point, the first bit's the sign bit, and then X number of bits are the mantissa, and the rest of the exponent. Maybe I mixed that up, but they'd written all this stuff from scratch, which is really weird, because I was like, did casting not exist when you wrote this? Did somebody not know how to use cast? So I specifically went looking for cast, and it's in there. Let's see if I can find it. Here it is, right here. So that exists. So somebody did a whole bunch of work for no reason. So that was one of my things I was super interested in. Why did they do that? So some other things, is there a way to build an executable? I really have no idea. So another thing that I found deeply frustrating, let's say I go and I put, say, serial port init on there. So in LabVIEW, you're very used to saying create constant here, like these serial ports. Well, it doesn't exist. There's no way to do this. So what exactly is in these terminals here? This big structure here, this big cluster. How can I get that? Can I copy it onto my front panel? Yeah, that works. But it's kind of cluttering the front panel, and if I don't need to change those, how do I turn it into a constant? There's no way to turn it into a constant because that feature doesn't exist yet of turn this control into a constant. So you're sort of stuck with everything on the front panel, or laboriously trying to recreate this cluster by hand, which is, it's painful sounding, and it's even more painful to actually do because you don't have any idea what these, what's the underlying structure of it. So that's pretty frustrating. See. Yeah, undo, I can't undo this. It's stuck there. So that's pretty irritating. Let's see, what else have I? I made a little list of things to make sure I didn't miss any of these crazy features. LLBs exist. You can just save this as an LLB. Save as. Now you're in this VI library, and you can call this untitled or something. So, so that's. I didn't realize it was that early that LLBs appeared. So, and then somebody, it might have been Ed, asks me, does instrument.lib or user.lib exist? And no, they don't. There is vi.lib, but in here is none of this sort of stuff you put your own personal stuff in. It doesn't exist. And I don't know that there's any way to make a sort of a personal thing on the palette. These are all very much sort of the built-in things, and there's no way to recursive VIs are not allowed. So I didn't even try that. So yeah, there's no way to add your own things to the palette, or even use a third-party tool. You just have to go and manually select them. So anything else you want me to try here in Windows or in ancient LabVIEW?
I remember, I can't remember if it was 3 or 4, but you can build the executable.
Okay, yeah.
Yeah, you can. I did build that, but I don't remember it was in 3 or 4.
No,
Okay.
yeah, I built some in 4. There's no
Yeah.
runtime engine.
Yeah.
You built the full program is the executable. No external stuff required except the 2 little drives, the DAC and
Yeah,
this drive you had in there. That's the only thing you needed as driver.
Yeah. I was
As
reading,
you remember, I don't remember that, but yeah, it was a long time ago.
yeah, I remember reading that in certain versions, and it might have been only on the Mac, you could take, you could somehow take the runtime engine and mash it together with your executable, so you only had a single file that you had to move around. And I didn't quite grasp how you did this, but it sounded very interesting. Like I wouldn't have to distribute anything with my program except the program.
So you can run it from a CD, for example.
Right. Yeah, or a floppy more conceptually because it was that old. But yeah, it was an interesting idea, and if I could find the article, I might, it might be interesting to see if I can actually get that to work on, another virtual machine that doesn't have LabVIEW installed on it. So.
So prior to executables, did you guys, you had to install the full LabVIEW for people to use your applications?
I assume.
No, you had the application builder, which is extra, but then when you built it, you had an executable, need no LabVIEW needed, nothing, no runtime.
Yeah.
It's just a standalone program.
Yeah.
I built one of those in probably '96, and it was running for like 25 years on the same Windows 95 computer.
Wow.
Controlling in a little instrument, Yeah, 100 megahertz Pentium 1.
That's faster than my first PC. My first PC was a 90 megahertz Pentium 1.
That was probably a 486.
Yeah, right now.
Yeah.
Yeah, this is for my thesis. This is I think it's LabVIEW 3.1 or 4. They have the spectra of a lot of hydrocarbons, and you can tune your laser system to shoot on the different wavelengths.
Okay.
Yeah. I feel old now. Shit, that was a long time ago.
Yeah. I think it was version 8 or so, somewhere in the range of 2000 that I got involved in LabVIEW. So,
I think that was a big jump when 7 came, right? 7 was so much better than 7 was super stable and super good. I remember, right?
Yeah, I don't quite recall exactly when I got involved, so I can't really speak to how terrible it was before or after. So, I do remember that I was very weary of it was an environmental chamber with a HP 9000, I think it was, running Rocky Mountain Basic, and that was connected to a plotter and this environmental chamber over GPIB. The plotter was on serial or on parallel, I think, and then there was also a ThinkJet printer, and it was this infuriating thing to use, and that's what inspired me to learn LabVIEW. So, and I'm like, I'm getting rid of this whole thing. I'm going to throw it in the trash except for in the environmental chamber, and I did, and it still runs, still out there. So I had. Go ahead, Peter.
I was just going to ask a question. I mean, I'm a little younger than you guys. I know back in the day, you didn't have multi-core processors to play with. When did parallelization or multi-threading, when did that come into play for LabVIEW?
That came way before the multi-core CPU, so LabVIEW was way ahead there.
Yeah, is it in here? I wonder. Let's go look.
You make your own race condition.
Yeah.
Actually, there's some stuff, you know. I mean, then you had to run. I mean, I had to run a separate computer with a separate LabVIEW program, and then push that. Actually, push it with Ethernet. I think it was TCP to the other one to get some of the calculations done. So it's separating between different computers, actually.
But even in LabVIEW 4, you know, I had my data acquisition going in a different tab. I was not tab, but a different screen. I was able to subtract 2 spectra, and I was able to print everything in parallel, right? It was really working really well compared to what was available back then.
So there's no parallelization here, but you can obviously write 2 structures that do things in parallel for you. And that's one of the great things about LabVIEW is it's very simple to parallelize things. So I had some grandiose plans to have a demonstration of this talking to some actual hardware, because I have a vintage, same sort of vintage Tektronix TH, and so I have a serial cable I made for that, and I have that talking to a PC over USB, and but I could never get it to work. The scope talks to the serial converter, that talks to the VM, that talks to Windows 3.1. You can go into hyperterminal there in Windows 3.1, and you can issue commands *IDN, and it works forever. But when you go to LabVIEW and try and actually get it to do *IDN, just read the identification out of that device, it'll work once or twice, and I think once I got it to work about 3 times or 4 times in a row, and then it just freezes, and the only thing you do is stop the VI and start it again, and then you get 1 or 2 more tries. So is there some setting in here that I'm failing to deal with properly? So in here there's serial ports. You can say enable a serial port and port 1, and then in here where it says port address, you type in type COM2 or something like that. You know, is there some port mode here that I should be setting differently? Would that make it work better? Or is it just the fact that it's a ridiculous chain of things trying to connect them all? So I don't know. I never got it to work. It was pretty frustrating. So I was really hoping to have that live and running here for you, but sorry, it never got it to work. But you know, if you did have code that was talking to something like that, you could at least look at the code and see what people are doing with it.
So I was going over my notes, and actually, if you have Windows 10 32-bit, LabVIEW 3.1 still runs.
Okay. Huh.
And so I'm in a virtual machine.
Okay.
And when you try to install it, then it wants to install NTVDM, probably some extra module that's required, some memory management.
Okay.
Then it runs and installs, and I can share my screen for 1 second. Let
me see how.
Yeah.
Let's see. It's that thing? No. It's interface is a bit confusing. Let me come out of. I'll have to stop sharing, and then let's see, chat participants. Yes. All right. You should be the host again, so you should be able to share.
Okay. So, yeah, I just share a window. So that's actually what in the Champion forum. So I did Windows 10 32-bit VirtualBox, and then I get a couple of hurdles, but it was Windows 10. It doesn't run at all on 64-bit. And then somehow it wants to install NTVDM, which I okay.
Virtual Disk Manager?
I don't know what it is. I need to look it up.
Yeah.
And then afterwards, that demo was running.
Wow.
And basically it's a demo. It's real LabVIEW, has a couple of applications you can click. And at the end, you can create your own. The only thing is you cannot save them.
Right.
That's what the demo is, but everything was running.
Huh.
Yeah. And this 3.3.1. Yeah.
Okay.
Yeah.
Wow.
Yeah, see,
No, I'm not the only weirdo doing this stuff.
They had demos for bubble sort. See?
Yep.
In there, everything.
Huh.
Yeah. So, okay, let me stop sharing. Okay. So I still have these files. If I can send them to you, I have a zip file with the demo on it. You can just install it on your virtual machine.
Yeah. Let's see. Yeah, that sounds like fun too. Yeah. And one of the reasons Windows 10, you need a license for, so you'd have to figure out some way to license Windows 10.
No.
Okay.
No, Windows 10 you get on the virtual machine.
Okay.
You can run it forever without a license. The only restriction is that you cannot change the background.
Oh, okay. Wow. Yeah. That's a pretty trivial restriction.
Yeah. Yeah, because they know that everybody, like in Asia, in the low-income countries, and like Bangladesh, they all install it and run it hacked copies, right?
Yeah.
So it's safer if they don't have hacked copies.
Yeah.
Yeah, Windows 7 was still pretty restrictive, but Windows 10, it's wide open. They want everybody to use it. You know, it's only. So I never bother activating Windows 10. I built dozens of virtual machines doing beta testing, even though I do have a license, from a corporate license, from UCLA.
You can go to the Windows website, or somewhere in Microsoft, you can download a pre-built Windows 10 installation. It's only good for 60 days, I think. So if you want to test things out that way. So that's one way to do things, but it doesn't work forever. Another thing you can do, which it's not activated on this machine, is Windows. It's called Windows Sandbox. So in here in your Start menu, you'd have to go there in the Install Features and install Windows Sandbox, and then down in here you end up with this Windows Sandbox, and you right-click on it, and you say Run as Administrator, and you get a totally blank version of Windows. It's got nothing else installed on it, so it's great for does my installer work correctly? Does everything go where I need to? So, and then as soon as you exit it, it destroys everything. So, it's
Regarding virtual machines, I have a question. So usually what I do is, maybe Christian has a good suggestions on this. Let's see, or some other guys. So every time it's time to upgrade LabVIEW, I build a new virtual machine from scratch, and I need to install not only LabVIEW, all the other freaking software I have, and then I build that and I test it out and see if it works, and then eventually I migrate and such things. But there's a lot of other stuff going around, and of course you can have a machine that you have most of the other programs on, kind of updated, and then you clone that, and then you add LabVIEW and such things. But now when they have this fantastic package manager, I was just thinking, maybe should I just clone what I have and then uninstall everything in the package manager and then install the new version. Wonder if that's going to work well or not. Sometimes I had issues, really weird issues on real-time systems when I've tried to cheat and not installed everything from scratch. But I don't know if someone has any experience of the package manager and moving between versions and such stuff.
Yeah, I don't.
I had some trouble with that. it was in a virtual machine, and it was sort of inherited from a previous virtual machine. And I even had to contact NI Help because it was specifically using like real-time module and the compact Rio drivers. And it ultimately, I found out that when I put things back on, I had not done it in the traditional order of LabVIEW, then the modules, then the drivers.
Yeah. Yeah. Okay. Maybe from scratch then still.
Yeah, maybe so.
Now I had some crashes, you know, and they were very seldom. Well, they were, but they were seldom, and no one could figure anything out. And NIL says we don't support virtual machines, you know.
Right.
So, yeah. Okay. Well.
So I've pushed this vintage LabVIEW virtual machine up to my GitHub page. So feel free to pull it down. I managed to make a typo in the title, so just ignore the fact that, or just accept that it's a typo and grab the right thing. So feel free to grab this version of, with LabVIEW ready to go. So if you feel like installing VirtualBox, you can irritate yourself in ancient LabVIEW.
Yeah, so back to the packages. One thing that I really didn't like, I mean, I tried installer with regular installer, MSI installer with the runtime engine. If I do a package, I have absolutely no choice that my users get the runtime engine with all the bells and whistles, all the modules that you can uncheck in the regular installer.
Okay.
So what I ended up doing is I'm making my own runtime now. And I call it runtime light. And you build an installer, you know, and then you just don't add any executable. And you include the installer. The application builder complains, hey, there is no file selected, but you can just ignore that and build it with just the things selected that you want. And it doesn't even install package manager or anything else. And it's like a 180 megabyte file that has everything in it that I need, nothing else. And I just tell people to install that. Of course, I have to do, with each update, I have to do a new one, but I think it's worth it.
So there's also a tool in LabVIEW called, and I did a presentation a couple years ago about it, with this installer thing that they have. Let me see if I can pull up NI Batch Installer Builder. So it's a free download. I think it's technically part of one of those professional or whatever they call them. I can never remember what the names of all these different versions of LabVIEW are. But you can install it, and that allows you to go say, here's a list of runtime engine. Here's your LabVIEW. In this example, I've got LabVIEW Runtime, DACMX, Serial, and Visa. And then that builds into a single file or a single directory. You can zip that up, and it installs everything correctly for you. Yeah, it's a huge installer. It's the 2 gigabyte nonsense that you're irritated by. But if you've got a whole stack of things and you don't, the thing you've done, Christian, is very light, but it's not super obvious what to do, I think, from a neophyte's perspective.
You need very little. You need a lot of installs, right?
Yeah, I need a whole heap of stuff. And this is, this has changed over time. I also install Foundation Field Bus. I install TDMS, the XL TDMS stuff. So it allows you to package all these things up at once. And then if you want my data acquisition program or whatever to run on your PC, you just run this installer. Yeah, it takes an hour. There's a lot of menus to click through, but you're done. You don't have to go make sure you install these 4 things in the correct order. It just happens. So it's out there. It's a tool that's available. It's a little klutzy, but hey, it's free. So.
Yeah.
I didn't have, that's all I had for presentation. So
Thank you so much.
yeah, thanks, Christian. That was really excellent. It's neat stuff.
Yeah, it was great. You didn't even understand those things, but we'll look into those maps. That looked interesting.
Yeah, the maps are really useful. You can do so many things, and even in the new array palette, there's some of these VIMs are actually map based. For example, remove duplicates from an array. There's actually map code underneath, and it's trivially simple to do that. It would be much harder to do from scratch with classic code. So
okay,
it's very nice.
Yeah. Anybody got anything else, or shall we call it a night?
Yeah.
Thank you.
Yeah, thank you, everybody.
Yeah,
Okay.
thank you guys. Have a good night.
Yeah, good night. Thanks.
Dinner's ready. Okay.
Thanks for letting me join.
Yep.
Yeah.
Good night.
Yes, bye.
Bye.